Very good afternoon to all the participants, and to join this critical session, to looking towards a new paradigm in the way the air conditioning is done in India. And we are from Adani. We represent Adani Cooling Solutions Limited, which is a 100% subsidiary of Adani Energy Solutions Limited. This group has been created about 2 years back with the intent of establishing large centralized district cooling systems across various types of category of large air conditioning user, like large mixed load developments, industrial SEZ, data center, residential townships, and large townships. So basically, I will try to cover all the aspects of why this sort of a district cooling system concept is very critical for adoption in India. What are its benefits? And we will also present a few case studies which will enable to understand the nuances of district cooling solution. What are the various benefits? What are the various and also we'll touch upon the various challenges which we are facing, and for which there are certain statutory support required, certain policy guidelines to be done. We have had certain progress, but we'll also talk about that. So I'm heading this the organization ACSL, Adani Cooling Solutions Limited. And earlier I was in the power sector for a long time, in Tata Power and in Tata Group, other companies. And then I was with World Bank for some time, and also in various other organizations in the leadership role. So I will stop here, and I will request the Gauravji to introduce him.
Thank you, Mr. Sarkar. Mr. Kapoor from
Thank you, Bhaskar sir, and a very warm welcome to all the attendees of today's webinar. I would really like to thank you, AEEE, for arranging such technical platforms where we can actually talk about innovative products, about the experiences of the applications which are still available globally, but it needs a lot of which still needs a lot of groundwork to be done within our country, India, and which can really help us in a long term for sustainabilities, also on the electricity platform and also on saving the water, which are the two critical factors for any country to grow. And it's my honor to share today's platform with Mr. Bhaskar. He has a great organizational experience till now, so it'll be really good to learn a lot of things from him. My name is Gaurav Kapoor. I'm a 2010 mechanical engineer, and I have been into pump industry from the beginning of my career. Currently, I'm associated with Grundfos for more than a decade now. I'm based out of Dubai, and in my current portfolio, I take care of district energy, which includes district cooling and district heating. District heating is very small for us, which is in Central Asia only, in Turkey, but majority is district cooling. For design of design support to the clients, to the contractors, to the consultants, in respective to the pumps. And I work for Grundfos. Grundfos is a renowned world pump manufacturer, which is based out of Denmark. We have around 66 manufacturing facilities across the globe, and more than 140 sales companies across the globe. In terms of production, we are world's number one pump producer. Like every second, we produce two number of pumps. And one thing which I'm really proud about Grundfos is being a private company. It's not a public listed company, and by the founder made sure that 5% of the revenue, it's not the profit, it's the revenue, it goes into research and development. So that is a very strong fact which has always kept us upfront in the market, that 5% of, so last year we did around 4.1 billion pounds. So you can imagine 5% of that is a good amount which is available for research and development, and which really help us to bring new products and new technologies to the market. In today's webinar, we will touch base on basically we'll look into a case study based out of India, why district cooling is superior than conventional system, and then we will have a brief or core understanding of what type of main large size pumps are being utilized in it and how to understand the pump curves associated with it. Thank you.
Gaurav, if I heard correctly, did you say 2 pumps per second?
Yes, sir. You're correct.
So by the time you spoke, another 150 to 200 pumps have already been produced by
Yes.
Dhronpur.
Yes.
Okay. So thank you, Mr. Sarkar, Mr. Kapoor. We thank you for your time and continued support and participation in AEEE initiatives. With this background, may I request my colleague Pramod to please set the context for today's session. Over to you, Pramod.
Thank you, Ritubrato, and once again on behalf of AEEE, a very happy new year to everyone and warm welcome to this webinar. I'm actually feeling very delighted to set the context today because of my fascination with this topic. I got introduced to district cooling 3 years back, and immediately I fell in love with this. It's an energy efficient solution. It helps in managing peak demand. There is an element of refrigerant transition, use of green, clean refrigerants. The solution can be integrated with renewable power. As Gaurav was mentioning, it also helps in water savings. It can utilize sewage water. It has very good reliability, so maintenance and performance degradation over time, unlike the conventional cooling system. That's not a big issue here. And there are very few solutions which bring so many benefits together. So I also had the pleasure to lead a project management unit that was established under the Energy Efficient Cooling EE-Cool program, which was a bilateral cooperation between India and Germany. And under the program, there were several initiatives undertaken to promote district cooling systems in India. When we talk about energy efficiency, often the discussion is on operational savings, but energy efficiency can also lead to savings in upfront investment. The key lies in integrative design, and if the solutions are carefully selected, sized, sequenced, then capex savings sometimes can be huge. And maybe Bhaskar ji and Gaurav will take our participants through some of those examples. In district cooling system, if we look at 7 or 8 years back, the concept was very limited, largely theoretical, and most of those projects were implemented in a captive model, which means the owner and beneficiary of the cooling projects were the same. But since the launch of the India Cooling Action Plan in 2019, I think as a country, we have moved the needle significantly. We have transitioned from viewing cooling from just as an appliance to now viewing it as an essential infrastructure, which then can be delivered in the same manner as country is working on electricity, natural gas, water. So a major milestone in the journey of district cooling system was the release of the district cooling guidelines in 2023, which GIZ and BE they launched, and AEEE played an instrumental role in development of that guideline. And following the launch of the guidelines, we see already a lot of positive signals towards how regulations are trying to, push more and more adoption of district cooling system. If we look at, for example, the Energy Conservation and Sustainable Building Code, ECSBC 2024, it explicitly mentions DCS. If we look at the draft National Building Code, which is under the process of finalization, again, there is a separate chapter mentioned on DCS. So these are all examples on how codes can start mandating such efficient solution, efficient infrastructure, which will be critical for creating the demand of DCS. Just a month back, Bureau of Energy Efficiency and GIZ together, they developed a district cooling roadmap for India, which sets out a target to achieve a cumulative DCS capacity of 6 million TR in next 12 years. So all of those things we see, there are discussions on establishment of a national competence center or a center of excellence on district cooling and to promote cooling as a service models. We see examples from states like Maharashtra, where electricity tariff for a district cooling system has been now mentioned as a separate category, so that the benefits of district cooling do not get eroded because of higher electricity tariff. There are states, Tamil Nadu, Kerala, Haryana, who are all working on district cooling in one way or another. So the technology is ready. We heard Gaurav, he mentioned about, Middle East. There are several other countries, Singapore, Dubai, who have promoted district cooling. In India also it has happened. It's just the merchant model and cooling as a service model is now gaining traction. The benefits of district cooling are known, and with the roadmap now in place, I think the focus for next 10 years is going to be only on execution, execution, execution. And how do we move from these captive standalone plants to these interconnected city-wide or locality, community-wide cooling utilities. So I'm really glad that we have two industry leaders, Adani Cooling and Grundfos, who are pioneering the implementation of this solution, and how this is going to shift the burden of upfront capital from the building owners to the operators and project developers. So it's again a good example to unlock the capital for other purpose and work towards a service model. AEEE is playing its part. We continue to promote the inclusion of DCS in various ways, whether it's urban planning, regulation, or through demonstration of projects. And let's hear from both of our speakers today how they are practically tackling this issue, addressing it through design, addressing it through various efficiency ways and different models to make this vision of achieving 6 million TR by 2038 a reality. So thank you everyone, and wishing everyone all the best. Back to you, RBS.
Thank you, Pramod. That sets up perfectly for the rest of the session. So, dear participants, that is all our attendees, we want this webinar to be very interactive. We will try to address all the questions that you have. Someone has asked if we will be sharing the slides. So we may not be sharing the slides, but we will be sharing the recording of this presentation of this webinar for sure. So, but on your screen, you will be finding a chat box as well as a Q&A box. Our request to all of you is that any hygiene issues, connectivity issues, you can always mention in the chat box, but it will be easier for us if you put your questions in the Q&A box. We'll try to club questions and take up as many as we can during the Q&A session that follows both the presentations. With that, I invite our first presenter, Mr. Sarkar, to share the screen and start the presentation. I'll let you know once your screen is visible, sir. You have 25 minutes for your presentation, and I will, if required, ping you at the 20th minute. Over to you, sir.
Thank you. I hope the screen is visible.
It is.
Okay. So once again, I thank you and welcome all the participants. I will do as quickly as possible and complete within the time which is allocated. So I will cover these 5 topics mainly. As Pramod ji said, that the context and need also I will cover, and the solution overview, cooling as a service, some case studies of some projects which are real life case studies which we are having, and key bottlenecks and statutory support which we are struggling for. That also I will cover. So we all know this, that there is a statement by the UN Secretary General that the era of global warming is over and the era of global boiling has started. It's a very strong statement, and this is backed by the data also. If we see this graph, we can see how the temperature has been steadily increasing, particularly in the last 2 3 years, 2024, 2025. There has been a significant jump in the global surface air temperature, which is an alarming rise, and if it goes up at this stage, it may cross 2.1 degrees by 2100, which is much more than the restrictive value of 1.5 degrees. So this situation is really alarming, and we need to think differently. And that is one of the basic, background information to start thinking why we need to really think about DCS. Now, these are a set of graphs. Many of these may be known to all of you. Particularly, these are all, most of it is also visible in the ICAP. But just I compiled a few data points to just give the perspective. So if we look at the per capita cooling energy consumption worldwide, you see US has a 5,653, and likewise the other companies are stacked. India is now at only 147 kilowatt hour per capita is the cooling consumption, which in average cooling consumption across India, which is much less than the average world average of 1539. This is one way good, one way also alarming, because one way is it shows that there is a huge possibility of increase which India has. And the other thing is that this increase will have a good toll on the energy infrastructure and the energy generation, etc. So that is also has to be thought through. So that is a very important piece of data. If you go to the next slide, just on the right side of this, on the top, you will find there are some bars. These bars are the percent cooling degree days. That is, it's a multiplication of the area of a country which is exposed to a temperature beyond 25 degrees throughout the year, multiplied by the population. So if you see the bar which is of India is the highest, that means India has maximum portion of its land exposed to temperatures above the 25 degrees throughout the year. And also, since it has a huge population, so the total percent cooling degree days is highest amongst the countries which have been shown. However, the penetration of air conditioning is one of the lowest, that is only 8%. This also corroborates the previous scenario, that there is a huge potential of increase, but as of now there's a meager potential which is implemented on ground. So the scope is potentially immense, the potential is immense. If we look at the ICAP's projections till 2037-38, Pramodji mentioned a few, we will see that there is a 8x growth which has been projected in the cooling, total cooling TR. Out of that, 11x growth is only in the space cooling. So 11 times growth is expected to happen in the space cooling if it grows at the as usual trend which is now happening. This would need 8 times refrigerant to be utilized. This situation is very alarming. And also, if it grows at that stage, the impact on the primary energy supply will be tremendous. It will be 4.5 times. If you look at the graph on the extreme right on the bottom, the increase in the temperature requirement in the gigawatt of power generation requirement only till 2030 is about 11% increase only for the air conditioning, to meet the air conditioning load of the space cooling. So this sort of increase, if it is allowed to go at this rate, it will be a tremendous impact on the country. So we have to see ways of curtailing it. And DCS, or district cooling system, is one of the very important components of which can enable us to curtail it by almost 25%. So when I had visited the COP30 this year, there were two objectives. One is tripling of the renewable energy and also doubling of the energy efficiency. So this is one of the elements or one of the initiatives of district cooling which can contribute significantly to doubling of energy efficiency across the globe. So we can save 120 gigawatt of generation if we successfully implement DCS all around. So if we look at this graphs, these are few numbers which are also taken from the ICAPS, and then we have projected DCS onto it. The green numbers are DCS. So if we see the projections of various types of air conditioning methodologies over a period of 2023 to 2037, 38 as projected in the ICAPS, we can see that the room AC growth is almost growing at 12%. The chiller growth, which is the primary ingredient for a DCS system, is expected to grow at a meager rate of about 9.6 or 10%. VRF is expected to grow at 14% and PSE 7%. So if this amount of growth is allowed to grow, then the load which is required, the installed capacity required to serve this would be 720 million TR by 37, 38 vis-a-vis 130 TR only, which was there at 22, 23. And this amount of TR would be required to meet the cooling load which is going to happen, which is 767 TR by 37, 38. Now, if we look at the scenario of what will happen if DCS is promoted. So if we can increase the growth of chillers from 9.6 to 19.6, that means if we increase a 10% growth of the chiller or by promoting DCS, what happens is that the same load can be served with 627 TR only. So that is the beauty of this, that so 629 TR can serve 767 in place of 720. So the installed capacity growth is required to go down by 1%. Total growth would be going down. What does this mean? This means that the same load is served with 13% less installed capacity, and there will be a saving of about 150 plus gigawatt of power also, if we can make this happen. And this 150 gigawatt of power is going to have a tremendous impact in selling of the electrical infra, including the generation, transmission, distribution, as well as the installation of the substations at every location for supplying or serving the air conditioning load. And 50 million ton of refrigerant consumption will be lessened. And also, if we look at the other way around, that what will be the if we are increasing to 720, which was the projection, how much of load could we have served? We would have served 950 million TR demand. So this situation is really something which actually provokes us to think that why we should not promote or why we should not install district cooling systems all around. So with this, we go to the next. So now I will take up a brief DCS solution overview. All of us know, but just to touch upon the points, the district cooling is a centralized plant. By definition, it is a separate plant in itself, which generates chilled water at 5 to 7 degrees. And the chilled water is provided through through insulated pipelines to each and every building which is there in the vicinity of the network of that DCS plant. And again, it goes into the buildings, then it goes inside the shafts and corridors and flats or the commercial or industrial units, and it captures the heat and comes back to about 12 to about 12 to 14 degrees back to the DCS, which is again cooled and again recirculated. So that is in brief the operation of the district cooling plant. So it has district cooling plant, it has distribution network, which has a combination of a supply and return pipeline network, and it is carefully controlled through a SCADA system, whereby each and every node is metered, and also the supply to each and every end user is metered. Just like we use piped gas, so it comes to every house. There is a meter, there is a bill every month. That bill is also measured. The meter is read, and the bill is generated, and instead of paying to the electricity department for the energy consumption, we pay to the district cooling service operator. And also there is a concept of thermal energy storage, whereby during the off peak or during the TOD, when the TOD tariff is less, the chillers can be used to generate chilled water and top it up in the thermal energy storage tanks, which are like batteries, which keeps that. And when there is a peak demand, at that point we can run lesser chillers, and we can use this chilled water already stored in the thermal energy storage batteries, and that also reduces the number of chillers or number of the units consumed. So if we see that what are the benefits in a nutshell, there is a reduced capex for cooling and infra, because the capital expenditure, the total units or the total TR units of equipment required in a centralized plant, due to load diversity of the various consumption points, is very low, and that is in a commercial we need about 70% of the total load requirement, which would have been consumed by conventional. And in a residential, it is as low as 20 to 25% of the total demand, for which we have to actually make provision for the plant capacity. So that actually reduces the capital expenditure for not only the cooling infrastructure, but also the associated electrical infrastructure by about 35 to 40 to 45%. So this is a first saving, or first positive impact of the district cooling system, that the capex gets lowered. The second is that these plants require a very low maintenance. These are large plants which are almost maintenance free compared to the conventional VRF or the split AC or air chiller systems, which require a significant amount of maintenance cost throughout its life cycle. And also the life cycle period of those equipment is also lesser. For split, maybe 8 to 10 years, for VRF similar, and for air-cooled chillers it may be 12 to 15 years, but DCS the chillers are 25 years and plus. So there is a overall life cycle cost reduction by 30 to 35%. The primary energy consumption becomes lower, because the normal conventional chillers or conventional air conditioning mechanisms, they have an efficiency of 1.1 to 1.5 IKW by TR. That means to generate 1 TR, they consume 1.1 to 1.5 kilowatt hour of energy, whereas a DCS system, it consumes about 0.75 to 0.8, so about 40 to 50% less. So the primary energy consumption is quite low. The peak demand is also lowered, because as I said, that it can be substituted with thermal energy storage, and also the diversity of the peak loads across various consumers can be clubbed together, so that the overall peak to be fed becomes lower. Another good benefit is that it uses STP water, and by using STP water, it also contributes to the water circularity, and the water which is almost every time it is wasted, even though it is now mandatorily to be used for flushes and for gardening purpose. But that also, even after that, it is seen that about 50% of the water gets wasted. So that water is consumed, And through consumption of that, what it also contributes is that if you see a building which has conventional air conditioning systems, the entire building is encapsulated by the heat which is generated by the air cooled outdoor units, and this heat raises the ambient by 4 to 5 degrees across those buildings and in the entire township. And that enhanced heat again creates a duration, which we say, which means it has to consume more energy to combat that additional increase in the ambient energy. So but whereas if we use STP water for the cooling tower, the latent heat is absorbed and the water vapor is released into the atmosphere, so the heating effect does not happen. It also adds to the humidity of the atmosphere, unlike a air cooled system. So that is the benefit of using STP water and a cooling water cooled system. The other is the refrigerant. Now the refrigerant, I will take a few minutes to discuss this. In case of if we assume that there is a 1 kg per every TR of refrigerant which is used. So if we are using a commercial system, in a commercial, if we use conventional, then we have to use the let's say 3000 TR of capacity, and say 4000 TR of capacity, and if we use DCS in place of that, we need about 70% less. So by design, if we have a thumb rule of 1 kg per TR, we are reducing the refrigerant consumption by 30 to 32%. That is first. Second is, this refrigerant is used in machines which are in a separate cooling plant, which is carefully monitored through leak detection systems, advanced SCADA systems. So there is zero leakage. On the other hand, if we go to any conventional system, we are very much used to the term that refrigerant leak, gas leak. So this gas is actually refrigerant which leaks into the atmosphere, and so that also is harmful, and it has a GWP. Suppose if we just go into a little bit of technicality, the VRF systems uses a R410A refrigeration normally, and so the GWP potential is about 2100. If we use a smaller size chillers, then normally the global warming potential is 1400. But in large district cooling systems, normally the refrigerant used is a very advanced olefin-based refrigerant, which is R1234ZD or something like that, which actually has a almost nil global warming potential, and ozone depleting potential already is zero. So this actually has a triple effect. So one is less quantity, number is zero leakage, number three is the refrigerant type which is used is low on GWP. So refrigerant has a triple effect if we use DCS, has a triple positive effect on the atmosphere. So overall, all this would lead to a 25 to 30% reduction in the carbon footprint. So these are the benefits of a DCS system. Just taking some time. So I will just touch upon the cooling as a service model, just an overview. First, I will talk about the Adani Cooling Solutions Limited and its ecosystem. So we are, as I said, we are a vertical under the Adani Energy Solution vertical, which is created, so that there is an integration between the distribution, transformer, transmission, power trading, and RE aspect of the Adani Group. And we have ecosystem which enables us to have a RE integration built to our power procurement. That means wherever we have to procure grid power, we can actually blend it with RE power from Adani Green, which helps to lower the the landed cost of the power which is being used. We have Adani Water Limited, through which we can get the advanced solutions for STP water consumption, STP water construction. We have Adani Digital Lab, which gives us the support of the SCADA and the in the control and instrumentation efficacy. We have the energy solutions verticals. We have distribution companies. We have transmission companies, through which we provide infrastructure support, also energy solution infrastructure. We have technical consultants on board who are renowned consultants in the UAE, who have made large district cooling systems made possible throughout the ages. So we have them on board. We are also members of the AHEAD, which is a World Bank platform with DPIT. Obviously, we are member of the AEEE, and we have several other memberships and collaborations with ASHRAE and other companies. We have tie-up with Mahapreet, which is a Maharashtra government company which is involved in large size developments of infrastructure projects. So this complete ecosystem helps us to also give many solutions which are allied and which add value to the district cooling solutions per se. So this is a picture of our tie-up with Mahapreet, whereby we are taking up new developments across Maharashtra through that platform. Now we'll come to the cooling as a service, which is also based on the design, build, finance, own, and operate model. So why we came to this base? Because when we initially started looking at this project prospects, we found that what is happening in the market. Any developer who wants to go in for a cooling water or chilled water system, first of all, he engages a design consultant who designs it for him. Then he engages a EPC contractor, gives him the design and tells that you develop it and you implement it. So the EPC contractor does it, and then once he has handed over, then he gives it to the O&M contractor, or mostly the facility management contractor, to maintain it. So in this process, what happens is that each of these three entities, they blame each other, and you cannot catch any of them, because the design person, whether he has done the correct design, the project execution person who has done the correct execution, everything boils down to the O&M person who actually bleeds or who actually bears the brunt. So, and he also says that I cannot be held responsible because I have not developed it, I have not designed it. So when we saw this, we thought that there has to be an end-to-end solution. So that's why we are involving very expert designers to design. Then we do the financing of the projects, we do the procurement, and we do the complete project management, execution, testing, commissioning. Then we do the maintenance for 25 years, so that the entire thing is on our bucket. So I cannot blame anybody. And also the developers and the end users are completely sort of enveloped from the headache of designing, or from the headache of the management and running the plant. And we have the central command center, metering, billing, and customer support to give all the support to this system. So this is the complete cooling as a service. Just to also add on to it, that when we are doing the capital expenditure, in most cases we do the capital expenditure up to the entry point of the buildings. However, our O&M covers the entire thing, even though inside the buildings we are not developing the inside pipes and the corridor pipes, and inside the flat infrastructure of indoor units, etc. But for O&M, we cover the entire end-to-end, because we don't want the end users to see two different agencies. One, they will call for IDU, they will call urban company, and for the chiller, they will call us. So that will be complete chaos. So we give the end-to-end solution of maintenance. In some cases, we give end-to-end solution of the capital expenditure also, based on the requirement. So this is our end-to-end cooling as a service. Now, just to have one more topic of part on this, how do we bill? So we have four areas of ownership of the costs, which include the first is the capex, which is the, as I was saying, that the plant, the pipeline up to the heat exchanger in each building is in our scope. The fixed operating expenditure, whereby the maintenance, the manpower, the spares and the AMCs, etc., which are to be done on a fixed as a fixed continuous basis. Those costs remain with us, and we bear those costs, and also the variable cost, which is of electricity and water costs. So these are all the costs which we bear. The capex is charged to the end users, which include the cost of the DCS plant, the piping and heat exchangers, etc., all the equipment, chillers, pumps, cooling towers, control equipment, piping, etc., which is normally charged through a fixed monthly recovery on rupees per square feet or rupees per TR of connected load. The fixed OPEX is also charged on rupees per TR, or in sometimes it can also be charged on rupees per TRH on the basis of actual pay per use. And the variable cost is necessarily charged on a rupees per TRH. Now, the inside the flat, the customer or the developer, he gets it done, the shaft piping, corridor piping, and the inside flat infrastructure. However, we do the O&M of that. These are some of the portfolio. When we started 2 years back, we had a very meager experimental project of 7,700 TR when we started, but we went around the market and we saw that internally within the Adani Group and also externally, there's a huge potential, as I was saying. So today we are having about 3 lakh tons of internal projects. We have started implementing about 60,000-70,000 TRs. About 1 lakh TRs are under implementation. And we have the pipeline, which is confirmed pipeline. Similarly, for external developers also, there is a total capacity which is about 1,52,000, which is the demand, and 1 lakh tons is the installed capacity which we are looking at. So total we are looking at about 3 lakh tons of installed capacity, which is what we are looking at. This has happened over a period of last 18 to 20 months. And this gives us a lot of confidence that this thing is going to stay. Now, I'll touch upon a few case studies just to show the improvement. So this is a mixed case which we are implementing, where there is a significant mix of retail and office infrastructure, where there is a 2,200 TR demand. There is a hotel, there are residential accommodations. So total requirement in terms of demand of cooling load requirement is 14,000. And had we installed chillers for the retail and hotel and also VRF system, which was being planned, we would have installed 14,305 TRs of conventional capacity to meet this 14,600 ton TR of load. But when we have implemented DCS, we have only installed a capacity of 5,500. Why? Because this 5,500 is the capacity required to feed the retail and office and the hotel, which feeds the residential during the night. So during the day, because of the complementarity of use, the same capacity which serves the retail and office and other establishments feeds the residential during the evening. So with that, we have been able to get a 62% reduction in the total capacity which we are installing. So that, as I said, brings in a huge amount of saving in the capital expenditure of cooling and the electricity infrastructure. The conventional systems have a efficiency of 1.04 on a very optimistic, first year sort of this thing. Whereas the DCS has a 0.8 in efficiency, where it is 23% less. This actually impacts the electricity demand also, which is significantly less. The electricity consumption is also significantly less in terms of because of the efficiency. The refrigerant capacity is also 62% less because of the lower capacity. Urban heat islanding in case of conventional would have been 2 to 4 degrees. Here there is no effect. Carbon emissioning, there is a 23% reduction, and which impacts in 0.1 million trees which are getting saved. So this is a case study of mixed use. Similarly, if we move on, we get a case study of
Mr. Sarkar, sorry to interrupt, but if you could wind up in the next 2-3 minutes, that will help.
Yeah. This is the last part. I'll just quickly sum. So if similarly for a residential, there is a saving is more, because the in a residential, as I was saying, that the installed capacity requirement is much less because of the overall load diversity. So 72% less, and that drills down into the other benefits as well. And in an industrial, because the industrial normally they use chillers. We are doing a large industrial plant of 45,000 TR, which is largest in the country. So there also we have seen that there is a significant reduction, which is corroborating with the facts which I stated. This is a large township illustration, whereby if we see that in a large township there are offices, hotels, residentials, malls, which would have needed a 44,000 TR of capacity had they been conventional. But in a DCS system, we only utilize, we would have installed 30,000 TR based on the peak demand, complementarity, and that would have saved a significant amount in all aspects. So this is one. And then next, I will just touch upon this, that there are various issues and concerns which we have been facing. One is the tariff, which we had been struggling and fighting with all the regulatory forums, and thankfully first time the DCS has been notified as the industrial tariff category by MERC. In fact, DCS has been recognized as an industry. That is more important, because earlier DCS was, nobody knew what is the DCS. If it's in a commercial establishment, it was thought to be a commercial activity. If it's in the residential, it's a residential supply equipment. So the residential tariff would be applicable, which is 14 to 16 rupees per unit in Maharashtra. If it's a commercial, then it will be commercial tariff, which is 12 to 14 rupees. But now, first time for all the distribution companies in this multi-year tariff notification, the MERC has been, we had approached the MERC, and there were, after a lot of hearings and objections of all people, that has been accepted. So this is one thing which will be giving us an edge over the conventional in terms of the consumption cost. We also feel, and we are working very closely with the Ministry of Housing, Urban Development, and also the DPIIT, that in the municipal norms, if we approach a municipality for laying a DCS pipeline, they say that this is not allowed. So there is no norm for laying of pipe through the roads, which is allowed for electrical infrastructure and all other infrastructure. And also there are large number of urban developments which are happening, large number of infrastructure developments which are happening, but nowhere there is a mandate of having a DCS, a land for DCS. There is a mandate of having a STP land, water cleaning land, and also electricity substation land, but no mandate for having a land for a common DCS. So that is what we are proposing, and we expect that policy would come soon. Mr. Pramod has already explained that NBC code is being amended and a chapter on DCS is being added. Now, the financial incentives to large, this is another area where we are facing a lot of problem, because as Mr. Gaurav is there, he would also agree that large OEMs, and it may be chiller manufacturers, pump manufacturers, they don't get the confidence to set up the plants for manufacturing large size equipment in India, because of two things. One is that the demand projection, or the demand they see, or the market they see, is very low to give them that confidence. And number two, there are no financial incentives or support mechanism to promote them or to motivate them. So this is also something which we have taken up with DPIIT very strongly, that we need to identify DCS as a public utility to be installed mandatorily in all the SEZs, all the townships, so that demand which comes from the government side is seen, and that confidence comes with the OEMs to start manufacturing large size equipments in India. And also sort of financial incentive structure has to be supported. So that is again. So with the Ministry of Environment also, a lot of points has been taken up, which includes the in the recognition of DCS for the green building, for the GRIHA, and for the IGBC lead, and also providing some restriction for using of the refrigerants which are damaging to the which has high GWP potential. So these are some of the things which we have taken up, and I wanted to also mention this. And this is a ruling which has come, which Mr. Pramod also said, that the Commission has agreed, and for the first time, that DCS is a needs to be encouraged, and it has written that it is essential to encourage such energy saving efficient applications, and that's why has decided to categorize under the respective industrial category, HT1 and LT3. So this is a big achievement for all of us, because this is going to be replicated as a precedence in all other SERCs as well. So that is all from my side. I think I have not exceeded too much of time, but I wanted to cover all the points. So thank you. I will stop sharing.
Yes, no, that's fine, Mr. Sarkar. We can, the presentation was very holistic, and I'm sure it sets the context for the next presentation as well. But before you go into that, we will do a brief Q&A for about 5 minutes, which will be moderated by my colleague Santosh. So Santosh, over to you.
Thanks, Mr. Sarkar, for the presentation. There are some questions in the Q&A box, so I'm going to read for you. You can accordingly answer to those questions. First question is about, like, can DCS operate independent of the grid by using waste heat instead of electricity to drive cooling systems? If so, how much difference in performance can be expected? So it's about utilizing waste heat.
Yes, actually, DCS originally, wherever chiller-based plants, or VAM chillers as it is called, were used, they had started with the use of waste heat recovery system. If you remember, DLF and other large developers, they had started this. But if you want to ramp up to bigger sizes, then waste heat recovery may not be sufficient. So waste heat recovery can be, or waste heat recovery, or RE, or thermal energy storage. These can be the means for reducing the dependence on high cost grid power, definitely. And those the VAM chiller mechanisms and others can be definitely used. But for what we are looking at is large independent chillers, where the size of the chillers are 2000, 2500 TR, 3000 TR, which may not be possible for waste heat recovery plants, which can run smaller units. So
refrigerant side, the use of refrigerant in the conventional refrigeration cooling systems. And one question is about, like, if we can CO2 as a refrigerant in the cooling systems for the chillers, and what are the other alternatives of the refrigerants, if you would like to answer that.
Yeah, actually, this is a very interesting question, and this is across the world there are a lot of R&D happening on this. Various refrigerants has various characteristics. Like earlier, refrigerants had a ODP. Now the ODP is zero for all. It is nil. It has been already removed. Now the GWP is the next point in question, and next layer which is coming up is those organic refrigerants like ammonia, carbon dioxide, and others, where there are different type of challenges which we face. Suppose like olefin based, I mentioned olefin based or ammonia based, there are these require a negative pressure system to be created. That means whenever they are to be condensed, they need a negative pressure. Due to this negative pressure, what may happen is that if there is slight leakage in the system, the atmosphere will be drawn in, the air will be drawn in, pulled inside the system, and that will be damaging the system with all the impurities which will go in. So they have that problem. Although NH3 and carbon dioxide are probably one of the best refrigerants, but they have like ammonia has a high inflammable flammability, so that it is also that characteristic of ammonia also has to be checked. Even the carbon dioxide that operates at a very high, that needs a very high pressure. So the system design which would have to be much more robust, so the cost will increase. So every refrigerant has a pros and cons. So a lot of research is going on as to which should be the most optimum, balancing the cost, balancing the pressure, balancing the flammability, balancing the GWP. So that is where nobody has an answer actually. But yes, every refrigerant has a very good plus side, and also there are some minus sides as well.
So one more question is about average cost or average per unit cooling cost for residential setups, and does that also covers the STV plant and water cost included? And one more question is that is industrial category appropriate for all uses? What about cases where most customers are residential? So you can combine the answer for both the questions.
The thing is that residential has been a challenge across the world. Now we have taken that challenge and we have tried to, push large residential, developments, including the Dharavi redevelopment which we are doing. It is very difficult to actually balance the cost of the initial capital expenditure because the normal conventional systems which are used in residential are split ACs, which are very low on cost. However, the DCS entire thing has to be done. But because of the very low capacity which is required, it can be made at par. So the capital expenditure, maybe around 250 to 300 rupees per TR around in a 250 to 300 rupees per square feet. I'm sorry, not per TR. So 250 to 300 rupees per square feet can be the cost of capital expenditure recovery. And in a residential, what happens is that whenever the developer is announcing a air conditioned flat, like a hotel, that you enter into the flat and it will be completely air conditioned ready, and that cost of 250 to 300 rupees compared to the per unit cost per square feet is hardly anything, but it is a big seller in the market. So that is why not many developers are coming forward. And on an average, the fixed O&M costs are about 2 to 3 rupees per TRH. That means pay per use. And also there will be about a 15 to 20% saving in the variable cost of electricity because of the less number of units consumed, as well as the per unit rate, which is much lower because of the industrial tariff and other RE substitution, etc. So there is a overall saving for the end customers. If you see, maybe they have to pay a little bit more per square feet at the beginning, but over a period of 2 to 3 years, that payback will come.
So there are more number of questions, but we are going to take this last one. Maybe you can answer in the chat after this, as we are running short of time. So the last question to you, Mr. Sarkar, is like beyond technology and cost, user acceptance remains a key barrier in India. So from Adani's engagement with developers, municipalities, and consumers, what are the main concerns stakeholders raise about district cooling, and what has worked best to build trust and long-term buy-ins?
Yeah, so it's a very good question. Actually, see, the point is, if you take developer as a most key stakeholder in this, because the developer has to agree to install a DCS. Okay, so there are two types. One is that if the developer has to create a DCS system in his basement, then he has to sacrifice some of the parking spaces which can be commercialized. That is one thing which is a pushback. He does not want to install. The other most important pushback is the headache of installing this entire system, headache of maintaining this, headache of running this, all the spares, all the manpower, all of this is normally developers do not want to entangle themselves in this for a long time. That is one thing which we have faced. So having somebody who is offering a cooling as a service is a very good positive feel good for the developers, because they know that all my headache will go, and all my the responsibility will be taken by a prudent and a renowned group in the country, which is Adani. So that gives a lot of confidence for the developers to come forward. Okay, so that is what we are seeing, that change coming from. And also the end users are happy, because over a period of time life cycle cost is very low. Because of this, maintenance cost becomes lower, the refrigerant top up cost is nil, then the refrigerant the equipment replacement cost over a period of 8 to 10 years is nil. And so they also have a end to end one single point who is dealing with everything, so they are also happy. But there are some legal issues. For example, the residential apartments are not allowed to do commercial activities. Okay, so most of it, if it is done in a separate DCS, which we are pushing for, a separate DCS plant, then all these problems are solved. Then it's just you're like pipe gas, you are getting it on your in your entry point at a certain cost. You take it, or or go ahead with your own system. But so with a normal, with a DCS, people are coming forward, all these issues are getting resolved.
Thank you, Santosh, for moderating that. Thank you, Mr. Sarkar. The number of questions that we get goes on to show the engagement level of your presentation, sir. So if possible for you, you can look at few other questions in the chat box when the other presenter is presenting, or the Q&A box. And if you feel some of the questions have been left unanswered, if you can leave a very short answer or give an email ID for them to get in touch with the participants, that will be helpful. Thank you. Otherwise,
absolutely.
Thank you, Mr. Sarkar, for the presentation. With that, I would request our second speaker, Mr. Gaurav Kapoor from Grundfos, to please unmute himself and share his screen and begin his presentation, please.
Thank you.
Thank you so much. Thank you, Bhaskar, for such an informative session, and especially for leading and pushing DCS into India's at municipality level in India, which will really help us to reach India to reach their net zero goals before the targeted years. Please let me know if you can see my screen.
Yes, we can. Please go into full screen mode.
Thank you. So today's topic for today's knowledge sharing session is mastering pump selections. As I conveyed, I belong to Grundfos. I work in Grundfos Pumps, where we manufacture centrifugal pumps. And the agenda for today is we'll quickly look into district cooling, because sir has already covered majority of part of it. And then we will jump into introducing split case pumps, which are the main heartbeat of any DCS. These are the large size, mammoth size pumps which are used to make circulation of large amount of flow. For example, 500 liter per second, 700 liter per second at 35 meter head, 45 meter, 50 meter head. These are the machines which helps in production of water through chillers, deliver it to the end users, and also in the cooling towers. Then we'll quickly look into duty point selection. This is very important to understand that if you are going to buy or you are going to use a split case pump in DCS, how you should look at the pump curves, what should be the duty point selection for it. And we'll end today's presentation by also understanding briefly what are the testing standard associated with these machines or these pumps, because when you are going to procure or look at these machines, you should also understand that what type of testing or test certificates you should also request from the manufacturers to make sure whatever you need in the project is being delivered. Because DCS is all about efficiency, about sustainability. So if any efficiency standards are being committed, it should also be delivered at site. And which is also very important for CAPEX and OPEX calculations, which are being done prior to any district cooling plant is designed or established in any municipality or a district town. Now, district cooling, just a touch base, it is a centralized large size HVAC cooling plant where the production happens with the help of chillers. The chilled water is distributed with the helps of pipes laid out in the ground and being consumed by the end customers. It can be an industry, it can be a residential, it can be a hospital, it can be a mixed use building with the help of energy transfer station, which is nothing, just a heat exchanger and a set of pump, or directly connected to the buildings. Now, district cooling versus conventional cooling systems, it has already been discussed. DCS is way more sustainable and consumes very less kilowatt per ton as compared to other cooling technologies. As we can see on the top right of the curve, district cooling at an average, this is a old sheet, but currently if you look, it consumes 0.75 to 0.8 kilowatt per ton, whereas if we compare to the split units, which is the majority share in India right now, is 1.73 kilowatt per ton. And the other major benefit, besides all the factors already been conveyed by sir, is the aesthetics, which has also been touch base, that you remove all these machineries from a connected building. So you get a lot of space left for parking, or on the roof if you're using cooling towers, you don't need that, or air cooled chillers or VRF. You remove everything and you can maybe make a running jogging track or a swimming pool on the rooftop, which really ables to help developers to sell their properties with premium features available within the building. Now, how it actually worked out, how DCS has actually worked out. So this is the Gift City. It's a screenshot which was available with me from a presentation from Gift City. So if you look at the Gift City in Gujarat, it was designed for 200. The total required cooling capacity is 240,000 tons for a total built up area of 62 million square feet. Whereas but with the help of DCS, they were able to, with a 70% diversification, they needed only 168,000 tons of refrigeration, in which they further only installed 145,000 tons of chillers, and rest of the diversified load is being handled with the help of thermal energy storage. Now, by using DCS instead of a conventional system, they reduced the chiller capacity from 240 to 145, which is approximately 40% saving straight away on the chillers. And if we look at the power requirement, which was around 240, has been further reduced down to around 125, that is 50% saving on the electricity. So it clearly showed, this case study which has already been executed within India, that DCS is able to save 30 to 40% on the chiller capacity, which further helps you to reduce your refrigerant requirements, no leakages, ODPs, depletions. And also in the electricity, it really helps to save around 50% on the electricity if it is compared conventional system to DCS system. The core need within any district cooling network or district energy network is efficiency and reliability. And what does it mean? What does we mean by it? It means it is like any other services, municipality services which are being supplied to any industry or your home. It needs to be efficient. It means we should be able to deliver this service at the lowest possible cost, and it should be reliable, because we cannot justify that if the electricity not reaching to your home or to any industry, or water not reaching to your home or to any industry. Similarly, DCS needs to be very much reliable, that the chilled water should be able to reach to your home, because it is a factor of comfort for which it needs to be highly reliable. Now, if we look at district cooling application for from pumps perspective, where the pumps are being used in a district cooling network. So obviously in the main district cooling plant, you have process pumps, means primary pump, secondary and condenser, large size process pumps, which we will discuss in further slides. Then cooling tower makeup pumps, then thermal energy storage charging and discharging pumps, makeup water pumps, chemical dosage pumps. Then besides the main district cooling plant, there are TSE polishing plants also. So TSE, as sir talked about, treated sewage effluent or grey water reuse for cooling tower application. There also a lot of pumps are being required, and as a mandatory in few of the countries in the world, TSE is mandatory to be used in a district cooling plant to save on the water requirement in the cooling towers, because a lot of water gets evaporated during the operation of the plant. Then gray water TSE network, it means the gray water which needs to be reached to the TSE plant. There also the pumps are required. Then there are pumping substations also. Sometimes that's more on the district heating sites or very large uh, uh, piping network of district cooling, where the booster pumping substations comes into the network. What does it mean? It means if the network is too large, where the secondary pumps cannot push the water till the end of the building, there will be a small pumping substation within the network to further pressurize the chilled water to reach to the end of the building. And obviously the connected buildings to district cooling, there will be pumps required in those buildings also for circulating the water within the building. There are different type of connections available. It can be directly connected or indirectly connected through the help of heat exchanger system. Now, looking at the main context for today's is the type of pumps which are being used in a district cooling plant is known as split case pumps. These are the large size, huge mammoth pumps, and the main process pumps, which are primary, secondary, and condenser application in any district cooling plant. These are the type of pumps which are used. Why are we call them split case pumps? Because as the name suggests, split case, the casing opens and splits into two halves, either horizontally or vertically. It means if you open these bolts, as you can see, the top half will come up and the bottom half will stay in the piping itself. So you do not need to touch the piping, only the casing comes apart, and once the half of the casing opens, you can access to all the mechanical seal, bearing shaft, impeller, everything can be visually checked, and if it needs to be repaired or replaced, it can be replaced. They are also known as axially split case pumps or between bearing pumps. You never need to touch the pipes are always connected. You can access all the components within the at the site itself just by opening the half of the casing. Now this is how the pump looks like when you open the top half, or when you split case opens the splitted casing. You can access the complete shaft arrangement, impellers, wear rings, and when the mechanical seals and bearing also. We call it double suction design. Why double suction? So this is the suction side of the pump, and if you see, this has a ship type hull structure. So when such large amount of water is being pushed through the pump, it is equally divided on two ways and enter the pump casing from two sides into the impeller. If you see, this is a double eye impeller. It is like two impellers welded back to back, but it's a casted impeller. It is designed and made in such a way the water enters from two sides of the impeller and gets out from one way. When this happens, the all the forces balances itself, because water is equally split into two halves, and by doing that you reduces a lot of forces on the pump, and the life of the parts and the pump goes very high. In general, the design life of split case pumps is around 25 years, and they have a very low maintenance, regular maintenance or failures if it is operated and maintained properly. Now the other point which we need to be always remember is double volute. This was double suction, and this is double volute. Double volute, if you see, there is a small casted mechanical metal casting happens within the casing itself. So this thin line, if you see, it's a metal casting, and what it do, it makes sure that the exit, when the water is exiting through the casing through discharge flange, it also exits in equal proportions. So this is double suction, where you have a hull shape structure, and if you see a straight line here, that's double volute. This is suction, this is discharge. This is from where the water goes in, and this is from the water comes out. Now this is single volute where there is no metal wall in between, and this is double volute where there is a metal casting within the casing itself. This is a very, very important point to note, because double volute design helps us to reduce the radial forces drastically low. So on this side, if you see a curve, the single volute uh, forces are shown with the red color and double volute with the blue. On the y-axis we have radial forces, and on the x-axis we have flow percentage of BEP. Now what is BEP we will understand. So let's imagine this point is the BEP. BEP stands for the best efficiency point. So any machine, any centrifugal machine will have a point where it delivers the best efficiency. It means it consumes the lowest of kilowatt to deliver you the maximum of output. Now for a single volute pump at a best efficiency point, the radial forces will be in the picture of around 18 to 20%. But if you look at double volute pump, across the operation of the flow from 0% to 150%, it's always lower. Sorry, it's always lower than the radial forces in a single volute pump. So that's why for large size pumps which are needed in a district cooling plant, it is always recommended to use double suction and double volute pumps, so that you can have very low radial forces and axial forces, which helps you to have very long life of all the components which are there in a centrifugal double suction double volute split case pump. Now they also come in the vertical design in case you have space constraints. So it's same vertical split case. Your suction and discharge comes in line. You open these bolts and you can directly access to the all the internal components of your pump. Now one thing which is always important to remember is that in vertical and horizontal split case, design wise they both look the same, but there are one major important factor is that non-drive end means this is drive end where the motor will be connected on the top. Non-drive end bearing is not your regular roller bearing. It is a sleeve bearing. This is how a real sleeve bearing looks. If you see the red design, it is lifetime maintenance free bearing. It is also it and why we need to have this sleeve bearing instead of a roller bearing, because the complete weight of the water and the accessories lies on this bottom bearing. So if it is a ball bearing, there were very high chances of failure, and this becomes a very weak point for the failure. So that's why if you're going for a vertical split case pumps, because of space constraint, you should always make sure that it's a pure vertical split case design with a sleeve bearing on the non-drive end. This is a very, very important point to understand. Now if you look at casing specifications, it is very important to understand that depending upon the static height of your building on the suction side, your pump casing should be designed in such a way, for example PN10, PN16 or PN25, and they should be tested accordingly as per ISO 5199, 1.5 times the allowable working pressure for 10 minutes. It means if you're buying a PN10 pumps, or if a PN16 pump is required at site, it should be tested at PN24 bar for 10 minutes as per ISO 5199. As per our experience, we have seen primaries and condenser applications to be PN10, whereas for secondary application, PN60 is mostly recommended. Now for the material of construction for casing, cast iron is more than sufficient for smaller size pumps, but pumps with large volute size or higher PN ratings, ductile iron is more suited. Whereas for aggressive liquids, for example, we are using seawater as a condenser water, super duplex or duplex stainless steel is always recommended. Now, one of the main important factors to understand in today's presentation is shaft sleeve and material of construction. So a few years before, shaft sleeve was a mandatory design parameter, because at that time the shafts were constructed of carbon steel, which were prone to which were very prone to corrosion. Now to avoid any corrosion, we were using a superior metal as a shaft sleeve of bronze or stainless steel. But disadvantages of using a shaft sleeve, that there was an extra component in the machine which will get wear and you have to replace it, and to replace it you have to open up the complete pump and take off the shaft and bearing. So that's why few years before, the new hydraulic designs have came up where you do not need a shaft sleeve, because we have updated the shaft material from carbon steel to SS420 or SS431, so which are highly resistant to corrosion, and as a result you have less failure point in your pump, which again gives you a very long and healthy life for your operations and maintenance. Now duty point selection is very important to understand. So on the left side you see a curve, so this is a pump curve, and then you have a parabola efficiency curve. So BEP point, as I just informed, is a best efficiency point. It is a point where the pump delivers the maximum efficiency, means it will consume the lowest kilowatt to deliver that particular flow and head. And this is very important to understand, because at that point your flow, your forces and vibrations and noise are the lowest. Now this is a chart which we have pulled up from one of the standards, which talks about where you should select your duty point. So duty point is nothing, it is what is the flow and head required to for your particular pump plant room. Now let's say your duty point is this red arrow, and it is recommended always to select this red arrow within the preferred operating range, which is 7 to 110% for any conventional system, means where you're using a chilled water with standalone chilled water for building. But if you talk about DCS, it is very tight. It is recommended to have your duty point within 90 to 110% of the best efficiency point. Worst case scenario, if you cannot able to find a machine which can have your duty point within 90 to 110%, you should select a pump not less than 80%, because this is the range where you will have the best efficiency operation. Even at the lower speeds you will have the less noises and less forces and less vibrations, which will give you a very long maintenance free and healthy pumps, which will really help you to reduce your opex and also good for your operation and maintenance. Now how to check this 80 to 100%? It's very easy. Whatever your duty flow is divided by the BEP flow, majority of the manufacturers give them in their data sheet, but if you're unable to find it, it is very easy to see. You look at the efficiency curve, wherever it is peak, you just cross reflect it with your pump curve, and you can see your duty flow to BEP flow ratio, and there you can have the this particular range of 90 to 110%. Now this is the reason, as best efficiency point, your relative load, as you can see, is 0, and as you move far away from the BP point, your radial forces increases drastically, which is not recommended. Now quickly looking into the testing standards. So the centrifugal pumps are the performance testing, means the flow and head and power and efficiency, which is given on the data sheet. When any manufacturer issues a data sheet which has flow, head and power and efficiency, and when you receive that pump, you need to cross reflect it by understanding whatever we have requested for, whatever has been finalized, whether we are getting that machine or not. It is tested through a standard known as ISO 9906 or HI 14.6. Please remember, HI 14.6 2011 edition is the latest, and 9906 2012 is the latest edition. You should always get the data sheets from the manufacturers based on any one of these standards, and they should clearly mention whether they are giving you 3B, 2U, 2B, 1B, 1E, 1U, the acceptance grades which are mentioned here. And if you look on bottom on the columns, these are different grades available. So TQ means tolerance for flow, TH tolerance for head, TP tolerance for power, and T eta is tolerance for efficiency. So these are the tolerances which are allowed within these testing standards. Now for district cooling process pumps, the large size pumps, grade 1E is recommended, which you can say here, which says the flow can be plus minus 5%, of the data sheet or the decided data sheet, the head can be plus minus 3%, the power can go plus 4%, but efficiency cannot go negative. It needs to be either same or higher than which has been given in the data sheet. That so grade 1E is generally recommended for process pumps, whereas for other ancillary or general pumps, grade 2B or 3B is easily used. Now, the other important point is NPSHR. Now, you all may think ki HVAC is a closed network and you do not need NPSHR testing. No, on the cooling tower side, the condenser pumps are the open loop. So it is very, very important to also have a NPSHR testing required. If the cooling towers and the condenser pumps are, the height difference is not much, so it is recommended to also have a NPSHR test done. Please note, as I said, ISO 9906 2012 or 14.6 2011 should be clearly mentioned on the data sheet or the test standards, because before these standards the negative tolerances were allowed in NPSH, but after these latest standards the negative tolerance from NPSH has been removed. The other point which I just quickly wanted to inform is that in general HVAC standalone buildings of 2000 ton or 4000 tons, as per industry standards, a difference of 1 to 2 meter between NPSH available and NPSH required is okay. The cavitations will not happen. But that does not stand for large size district cooling plant where the flows are very high, because the suction energy ratio or the suction velocities are so high that uh, the difference of NPSH-A versus NPSH-R of 2 or 1 meter does not work out. We have done this exercise for more than 20 to 25 plants in last 5 years, and now as a standard for large size DCS, they say the ratio between net positive suction head available to net positive suction required is minimum 3 to 4 times, so that the cavitation does not happens. Cavitation is a very, very common and factors which we have seen in district cooling plants across the globe. In last 5 years, when we started doing this calculation of suction energy ratio and improved the NPSH-A to NPSH-R to 3 or 4 times, all of those issues has gone away, and the life of the pumps have gone very high. And the last test will be vibration testing. It is also very important that the vibration is being tested in the factories as per ISO 10816 or ISO 5199, which really make sure that your machines or your impellers and your shafts are very well balanced while manufacturing, and it gives you again a longer life of the pump and lower maintenance breakdowns, or lower maintenance cost, or lower apex. With that, we'll come to the end. If we have any questions, I'm more than happy to take it. I rushed a little considering the time available to us.
Thank you, Mr. Kapoor. We do have a couple of questions, and similar to the previous presentation, my colleague Santosh will be moderating the Q&A with you.
Sure.
Over to you, Santosh.
Yeah, thank you, Gaurav, for the presentation. So I am going to read out the questions asked in the chat box for the question and answer this tab. So one question is about from Sachin is about like what VFD based pumps. What about VFD based pumps where were at low operating speeds we are not able to make BEP break-even point, and this is common on secondary and ETS side. So I hope you have understood the questions, but yeah.
No problem. It's a very interesting question. Particularly if we discuss about this particular point, it'll take another half an hour for me. But just to understand, when you make a selection within 90 to 110% of a BEP point at 100% duty flow, when you start reducing the speed of variable frequency drive, the efficiency drop also happens in the similar range. There is a graph available which you can reach out to me. I'll put my email in the chat box, which clearly shows that with the reduction in the speed, the efficiency drops also happen in the similar proportion. So even if we are running the pump at the lowest speed, let's say 12.5 hertz, the efficiency drop is very, very minimal if you make your selections within 90 to 110% of the speed.
One more question is like I think it's similar to the previous, but as district cooling networks expand, how do smart pumps, variable speed drives, and digital monitoring helps operators optimize performance over time, especially under part load and variable demand conditions typically of Indian cities? So,
Again, a very interesting question. One of the beauty of district cooling system, as Bhaskar sir also conveyed, is diversity. So, for a standalone building, let's simply compare a building which is a mixed use building. You have few shops and a residential building on the top, and you have a 5,000 ton chilled water system installed. And then you have three residential building, one school, one hospital, and one mall, wind zone where district cooling has been supplied. Now, any machine, if for any pump or any centrifugal machine, if you run above 80% of its speed, it gives you the maximum efficiency. It's designed in such a way because there is a motor as a driver, so motor also has its losses. Now, for a standalone building, it is very impossible to run a single pump, let's say at the lowest flow, a single pump at 80% speed and above, because there is no such load availability. But for a district cooling plant which is connected with a thermal energy storage tank, let's say in the morning in the homes the requirement load will be very high, but as you move out from your home to offices or schools, the load will shift to there, and then maybe in the evening you go to the mall, the load will shift to there. So the load shifting pattern is there, which will really helps the district cooling operators to run the pumps and chillers at more than 80% speed. And worst case scenario, let's say it's peak winter. I'm sitting in Delhi right now. The winter is very high. I don't need a chiller plant, right? But district cooling will be required. Like in a hospital, you will be requiring HVAC. In some of the malls, in the lobbies, you will be requiring. So at that time, the thermal energy storage kicks in. So you start charging the thermal energy storage tank at the same time. So you're able to always optimize the speed of your machines and chillers more than 80%, which really helps to optimize the whole network. And obviously the sensors and digitalization and the data collection really helps in it.
thank you for the response. And the next question is almost similar to the one you addressed, but it's about like again considering the diverse load profiles in the district cooling system. So, what are the challenges in pump selection and network hydraulics for district cooling, which the planners should address at the early stage of the designing of these kind of crucial projects to avoid long-term inefficiencies related to the pumping solutions?
On the pumping perspective, so I'll not deep dive into the network designs or load diversity factor because it's a topic for another day. But if we briefly talk about the pump selection, it is not it is not very difficult, because if the let's take the same example. If you have three residential building, a hall, a mall, a hospital, and a school in one zone, which is total, if they had individual chillers of let's say 1,000 ton each, so 6,000 ton is the total requirement. Now, when they move to a district cooling plant, there can be a diversity of 60%. So this 60,000 into zero point 0.6 if you do, so you only have 3,600 tons of chiller available. So you straight away save on that thing. If this calculation is done properly, then the duty points which are given to a pump manufacturer, we can do the selections in a very precise way. The value which we pump manufacturers adds into is this process is on the so when the network is also being decided, you know how much head is required. Now the value which the pump manufacturers can provide is we are able to make the most compact pump with the maximum efficiency and the lowest kilowatt motor. That is the work which we pump manufacturers do. There has been a lot of projects specifically in Middle East where each pump is 710 kilowatt into 18 6 into 6 3 18 pumps. So you can imagine that 700 into 18, if you do around 10 megawatt of electricity required. You do not have that much grid power availability, because so the we sit with the designers and consultant, optimize on the head and diversity a little bit and try to reduce it to 5 or 10%. So even if I reduce 10% of 10 megawatt, that reduces to 9.1 megawatt. the values are very big. So this is the game or economics of scale. So that is why if everything needs to be designed in a proper way with discussions across with all the stakeholders.
Maybe with one last question from the Q&A. So question is that how does territory pumping have effect on chiller performance?
Very good question. Again, it's a long topic, but tertiary pumping is it really helps by reducing not on the so if it is a direct connection, it means you do not have a heat exchanger before the tertiary pump, then it helps you to improve your delta T's. But if you have indirect connection, means the pumps are directly connected to the secondary network, the major benefit it gives is it reduces the head for your secondary pump. So by doing that, you are able to reduce the total PN rating of the system for primary and secondary and the chiller side. So imagine if your building is, let's say, 160 or 100 meters height, the tertiary pump, and if you put up a heat exchanger, will break the pressure in between, and your chiller side and secondary side network doesn't need to be such highly PN rated. And second, when we do economics, we do the OPEX and CAPEX calculation. Tertiary pump individually can take care of the load variation within the building, which helps the chillers to stage in and stage it out properly.
Thank you, Santosh. Thank you, Mr. Kapoor, for patiently answering all the questions. If I may, there have been patiently, listening about 70, 75 participants. If in less than 30 seconds or 45 seconds, if there has to be one or two key takeaways for this audience, as you know, AEEE propagates triple sector leadership, which involves civil society, government, industry, and we work with a broad spectrum. And our audience base typically in all the webinars is a mix of these. So if there is one or two takeaways that you would suggest for people who have been attending this webinars, it could be from the perspective of a job seeker, it could be from a perspective of a potential partner, business partner. But I understand it's a wide spectrum, but if we have to sum up and summarize and give me one or two takeaways, what would it be? And probably I can begin with Mr. Sarkar and then come to Gauravji.
Yeah, thank you. See, this is a very interesting and very difficult question as well, because as we have seen, and I have also mentioned that there is a huge potential which is unfolding. Like we are today seeing the huge potential of AI and other initiatives which are ongoing. Similarly, for district cooling as a established concept of space cooling in future, there is a huge potential which unleashes a huge amount of opportunities, maybe for OEMs, like Gaurav said, for pumps and for chillers. It's a huge opportunity of business. People were not seeing this business. Everything was going to China and other countries who are actually reaping huge benefits of manufacturing this and earning the return. So that is a huge potential. The second is there is a huge potential for people to get into this specialized, whether it is engineering. We are having an absolute dearth of engineering professionals for DCS in India. So we have to rely on UAE and other countries. So there is a huge potential for people to adopt, adhere, embrace this sort of a profession, whether it is engineering, whether it is project execution, whether it is O&M. And I think it's just the beginning, tip of the iceberg. There's a huge potential coming up, and also the contribution or the impact it creates, maybe on the reduction or on the flattening of the demand curve, flattening of the generation requirement in future, flattening of the transmission infrastructure required to cater to the increasing cooling load, the distribution infrastructure, the client level infrastructure in itself is a huge saving to that country. So I think the country is going to be benefited tremendously if all of us put in our efforts. But as I have mentioned, there are certain policy and statutory norms and guidelines and regulations which have to be created, which are also available ready at hand from EOE and Singapore. They have already gone ahead. Those things are available. We do not have to create the wheel. There is already things are established and available. We have to adopt, and we can reap the benefits in future. And there is a tremendous opportunity for a nation, for every people in the nation, I can tell.
Thank you, Mr. Sarkar. Mr. Kapoor.
Bhaskar sir has covered everything, if you really ask me. It's the same words which I will just convey to everyone in India. 11 times the industry is going to grow in next 10 years. And imagine the amount of engineers. I know we have a lot of engineering colleges across India, but the amount of job opportunities right now in HVAC segments, they are also growing to grow 11 times. So just we should focus on improving our skills in design sites, in the operation sites, which is very, very much needed. And if you're really looking to open or set up your business, HVAC is the industry. So that's it from my side. Yeah.
Thank you, Mr. Kapoor. So before we wrap up, I'll just take 1 or 2 minutes. So one is we are privileged to have Adani Cooling Solutions and Grundfos as AAA members. And once again, thank you, Mr. Sarkar, Mr. Kapoor, for sparing your time and educating us and making this, spreading the message about district cooling solutions. We look forward to continue to work with Adani Cooling Solutions and Grundfos. Thank you, dear participants, for patiently being with us for the last couple of hours. AAA wants to engage with each of you. One way to do that is through our membership program. I understand there are representatives from startups, consultancy, educational institution, industry organizations. We can together work on white papers, syndicated research, projects and programs, co-curated events, and the options are limitless. So as a follow-up to this webinar, we will be sending a mail which will have the email IDs of our 2 speakers. You can get in touch with them for business networking or any other technical or knowledge queries that you might have. You will also receive a link with the YouTube video of this particular webinar. Finally, as you can see on your screen, our upcoming flagship event is the FEED Forum on Energy Efficiency and Decarbonization. This will be held in New Delhi in the month of February on 3rd and 4th. And I would strongly encourage, especially people in NCR and surrounding regions, to join us at this event. You have been aware of all the wide gamut of activities that AAA does. And you will find this to be one of the largest gatherings of stakeholders from the government, industry, academia, civil society organizations in these particular thematic areas that you see on your screen right now. So my suggestion would be to go to the FEED website, go and register yourself and book your slot. It is one of the best technical and knowledge sessions that you will find in these particular topics where AAA works in. Finally, with that, it's time to bid a very good evening to all of you. We do the series of ION Zero webinars, and probably the next one will be sometime in the month of February or March. You will receive an invite for that. Until then, a very good evening, and I hope to see you in the next webinar. With that, I would like to bring this webinar to the close, and thank you once again, participants and dear speakers.
Thank you so much. Thank you. And I must thank the audience for putting up beautiful questions, which I forgot to mention. The questions were very meaningful and very well thought. Thank you for that.
Very kind of you, Mr. Sarkar. And thank you,
Thank you,
Mr.
everyone. Thank you, everyone. Have a good day.
Thank you.
Bye.